Okay. So, good morning, everyone. Today we'll start with the lecture about the disposal of radioactive waste. As I mentioned yesterday, the radioactive waste, they are generated every time when we are working with any of radioactive materials. Uh, it includes not only nuclear fuel cycle, but other application of the radioactive materials like medicine or in research studies or in agriculture or whatever. So, and just a reminder that radioactive waste, so there are three main parts in the definition. So the wordings may be different in different glossaries, but still there are three main parts. So first of all, as far as their waste, there is no further use of these materials, at least with the current technologies. Yeah, so it's always about the current technologies. Maybe in future these materials can be recycled or can be used, but today no use for this material. As far as the radioactive, that means that there are some radionuclides inside or on the surface of these materials. But the important part also of this definition that the concentration or activity of the radionuclides must be greater or larger than the clearance levels that are established by the government in every country. So, and as we saw yesterday also, that spent nuclear fuel not always considered as radioactive waste. So if we are talking about the closed nuclear fuel cycle, then spent nuclear fuel is not radioactive waste. Anyway, it's just an example of the sources of the radioactive waste with their volumes and activity. Here, the activity is given in curie. So curie is another known standard unit. As you know, it is equal to 3.7 to 10 in order 10 of the becquerels. So it's how to say, convenient unit to measure activity when we are talking about huge activities. So you can see different sources, including so-called natural occurring radioactive matter from the ore mining and processing. It is radioactive waste from the nuclear fuel cycle, like uranium production, nuclear power plants, some radiochemical plants, and non-nuclear fuel cycle wastes like nuclear submarines, some isotope sources like medical application or industrial application, and some small part that even not listed here from the research operations. So only in Russia, you can see that it is quite a huge volume of the radioactive waste that are accumulated with quite a high activity. But when we will see later about the disposal of radioactive waste, first of all, we have to separate this waste like we do in usual life. Yeah, not in every country, but we are trying to sort typical waste for plastic, paper, I don't know, metal waste. More or less the same situation for radioactive waste, but in this case we sort the first classification, the first sorting is based on two main parameters. It is half-life of the radionuclides that are inside of our material and the specific activity. So there is recommended by International Atomic Energy Agency border between the short-lived radionuclides and the long-lived radionuclides. It is 30 years. For example, in Russian law, this border is 31 year because strontium 19 has a half-life less than 30 years. It's around 28.8 years, but cesium 137 is a bit longer, has a bit longer half-life, like 30.06 years. So if we took 30 years, then cesium-137 will be already long-lived radionuclide. So to avoid this misinterpretation in Russian law, we have this border as 31 years. Anyway, we have this limit or border between the short-lived radionuclide and the long-lived radionuclide. There is also another let's say, border for very short-lived radionuclide. Again, in Russia, it is 60 days, for example. In other countries, maybe some different numbers, but here it is 60 days half-life for the radionuclide. And then the specific activity of the radioactive waste. The lower the specific activity, the less dangerous are the materials. So there is some, again, limits or borders between the low-level waste, intermediate-level waste, and high-level waste. Again, there is some recommendations from the International Atomic Energy Agency, but every country established their own, its own limits and parameters for the classification of the radioactive waste. For example, again, since the last year in Russia, there is additional parameter, including the heat production of the radioactive waste, and thus there is a difference between the first class of radioactive waste and second class of radioactive waste. The first class produce also a lot of heat due to the decay of the specific radionuclides. So there is can be combination or some variations in the classification, but in general, the basis for all the classifications and sorting is this system. So the further sorting of the radioactive waste based on the aggregate state, solid, liquid, and gaseous radioactive waste. And then there is further sorting by the activity, by the possible ways of treatment of these materials. For solid waste, for example, it is pressing, cutting, are they flammable or not? Can they be burned or not? Can they be crushed or not, etc. For liquid waste, it's not only specific activity, but also are they homogeneous or heterogeneous? Do they contain organic liquids or only inorganic? What type of inorganic? What the salt concentration in the liquid in aqueous solution, etc. So again, for the further technical operation, for the further treatment, we need this classification, or let's say sorting of the materials for more efficient treatment of this waste, technological treatment of this waste. For gaseous radioactive waste, there is only one classification by the specific activity. And then again, we can make another sorting by the chemical nature. Are they noble gases, or it is halogens that can be absorbed by some chemical filters, or it is nitrogen oxide or carbon oxide, for example, or some other chemical nature. So again, it depends on the specific facility, on the technological processes, and we can add any other sorting as we so as it would be convenient for our technological processing of the radioactive waste. And as I mentioned yesterday, also the main issue in the disposal of any type of radioactive waste, it is a combination of the barriers. It is not, so the main barrier, of course, is just environment, the geological media, because it is the biggest barrier. The main purpose, the main goal of all the systems of the barriers to prevent the release of the radionuclides in the biosphere, to avoid any additional doses of ionizing radiation to the biosphere, to the people. So all the engineered barriers, of course, they have their own functional properties and goals, but again, the final goal is to prevent the release of the radionuclides into the environment. So the biggest barrier, as I mentioned, is the geological media. Depends on the type of the radioactive waste, and the repositories or disposals can be different. The deep geological repository is typical only for high-level waste. We will see further some other examples of the repositories. But then we have the solidified form of the radioactive waste, or compacted form if the waste were already solid. Then there is a canister or cask for our radioactive waste, and the buffer material that located between our cask and between the geological media. So it is like a multi-layer coat, or this Russian doll, matryoshka, that we call in Russia. So multi-layers. So, and the idea of the pre-treatment of the radioactive waste that we'll see later in the next lectures is, first of all, sorting of the radioactive waste, and also to concentrate, to minimize the volume of the radioactive waste, for better economic efficiency. And the effectiveness and the safe isolation of radioactive waste depends on three main parts. It is the site that we choose for our disposal. It is the characteristics of the repository of our building, let's say, or construction, and the waste package. And waste package, it is the waste form itself, and the container of this waste form. So, and there are certain parameters for every disposal, for every repository. There is a list of the waste acceptance criteria for the waste packages. Yesterday, Eduard Nikitin talked about these issues, and only the waste packages that comply with this waste acceptance criteria can be placed in this specific repository. So what this waste acceptance criteria? It is not only the waste form, it is all the characteristic, chemical characteristic, mechanical characteristic. It is the presence of biologically active compounds. It is the presence of the flammable materials inside the container, and all the other safety parameters. Very often it is not possible to make the chemical analysis of the radioactive waste with all these parameters. It's around 26 or something like these parameters. But there is let's say life hack in this case. It is written in the documents that if the facility where the radioactive waste were produced can prove with documents that through the whole technological process there is no flammable materials or biologically hazardous materials. If they can prove this, so uh, uh, they can avoid this chemical analysis of radioactive waste. So if they prove with documents that there is no possibility that these materials are in radioactive waste, then they can avoid this chemical analysis, and this waste package will comply with the waste acceptance criteria. So it is one way. So depending on the specific activity and geological conditions also, there are different types of the repositories. For example, for very low level waste and problems with the batteries. Just one moment, sorry. No. So yeah, again for intermediate level waste with the lift radionuclides, and for high level waste it is deep geological disposals. So the design of the disposal facility depends on the characteristics of the radioactive waste, on the period of the potential danger, on the geological conditions of the place of the site for future disposal, and of course the economical aspect is always important. So there are several energy, the lack of energy. Okay, it works. Okay, I'm here. So, next one. And before the construction and before the and during the design of the disposal facility, there are different safety modeling that are used for the prediction of the properties of the disposal facility, including the modeling based on the information about the geological history of the site, so it can the forecast of the evolution of this site can be done. Of course, hydrogeological conditions are important to avoid the penetration of the groundwaters into the disposal facility. It is heat and gas release inside the facility. If there are so again, one of the parameter in the waste acceptance criteria, it is the gas production. Yeah? So it is forbidden to have gas production, but there can be alpha emitting radionuclides. So alpha particles, it is helium particles. So if you have alpha emitting radionuclides, sooner or later you will have a lot of helium. So this overpressure also is also included in the scenarios. And of course, the final numbers that are important for safety assessment, it is the estimation of the dose rates in the biosphere for the population near this facility after proposed period of time. For example, again, depending on the potential danger of the radioactive waste, of the radionuclides inside the radioactive waste, this period of time can be 300 years or 1,000 years or 10,000 years, depending on the content of the radionuclide. So there are some examples of the disposal sites for radioactive waste for low-level waste. You see, it's like a building for the radioactive waste. It is the near-surface disposal facility, also for low-level waste. It is in Seversk, so it is Tomsk region. It is near-surface disposal facility for low-level waste in Ozersk. So it is the production plant Mayak, reprocessing of the spent nuclear fuel, the only one at the moment reprocessing plant in Russia, and the future deep geological disposal for intermediate and high-level long-lived radioactive waste. So it is the representation of the multi-barrier principle for this subsurface or near-surface disposals. We have our waste packages. There is a filling or buffer material between the waste packages. It is, of course, the layer that avoid the water penetration inside the disposal. And there is several layers on the top of the disposal. The final layer is just a grass layer with some soil to make the mechanical stability, let's say, of the hill above the disposal. So for high-level waste and spent nuclear fuel, there were several sites, several concepts based on different geological conditions. It was some volcanic tuffs. In USA, it was rock salt formations in Germany and in USA as well. And it is clay rock formations and granites in different countries. So the first step in all these different geological conditions, it is the formation or construction of the underground research labs to test the conditions. Are they acceptable for future disposal or not? Not always these underground research labs are constructed directly in the future site, but we'll see one example later. So volcanic tuffs in Yucca Mountain, as you know, this project was stopped already 15 years ago due to some safety concerns that it is not a suitable place for the high-level waste disposal for the very long period of time. And in Germany, you know, it is very anti-nuclear parties. They're very strong. So all the activities with the radioactive waste disposals in Germany, they are also stopped, but not completely. So it's moratorium. So that means that they can be started later if there will be changes in political situations. So now we can say that there are two main potential host rocks. It is crystalline rock and clay rock. All of these potential host rocks, they have different advantages. For example, these salt formations that are stopped in Germany but not in the USA. In the USA, you know, there is a waste isolation pilot plant that is technically, I would say, the first disposal of the high-level waste because, yeah, they call it storage or pilot waste isolation pilot plant, but I guess that finally it will be the final disposal of this waste in the USA. So these salt formations, they're good because they have very low water permeability. They have very good thermal conductivity that is important for high-level waste because they are hot, not only from the radioactive point of view, but just hot by the temperature. And these salt formations, they're self-healing. That means that if there is any cracks and the water start to penetrate, these cracks, due to the dissolution and the reprecipitation of the salt, heal the crack and water doesn't penetrate any further. But if there is a lot of water, that the disadvantage of the salts that they are soluble, and salts, they have no sorption of the radionuclides at all. So there is again the balance of advantage and disadvantage. For the clay rock, again, they have this self-healing effect because due to the structure of the clay minerals, they have this interlayer space, and when water interact with clays, water penetrates in this interlayer space, and the structure expanded or swells, and thus if there is any crack due to the swelling, this crack is healing by itself, so there is no, again, water penetration. That's why the clays, they are good because they have very low water permeability. Also, clays are known for their very good sorption properties. Again, we have medical medicine that we use when we have some problems with stomach, and this medicine is actually just purified clay. So because it absorbs all the toxic components and help us. Also, clays have very low solubility, but clays have very poor thermal conductivity, and clays can form colloidal particles, and colloidal particles, they are responsible for further migration of the radionuclides. So again, there is some advantages, very good advantages, but some drawbacks of the clays. And crystalline rocks that are considered also in Russia. Of course, the granites or gneisses, these crystalline rocks, they are very tough materials. They have very high hardness and stability. They are stable for billions of years. They have very low temperature extension and good thermal conductivity, but the significant drawback, disadvantage of the crystalline rocks, the formation of fractures and no self-healing effect of the granite. Yeah? If it cracks, it cracks. But anyway, nowadays, you know that in Sweden and Finland, there are already very close to licensing and commissioning two sites for the final disposal of the spent nuclear fuel. And in Russia, we also have chosen the crystalline rock formations in Krasnoyarsk region. And this is one interesting example of the underground research lab. Actually, it is not underground research lab because it is located in the mountains. And actually, it is very above the ground. I don't remember the height, but anyway, there is two lakes in the mountains in the Switzerland, and these lakes have different water levels. And initially, the tunnel was constructed. Yeah, here, sorry. The tunnel was constructed between two lakes by the company which produces electricity. So due to the difference in levels, there is a flow of water and turbine rotation and generation of electricity. But it was later so agreement with the National Nuclear Agency in Switzerland that this tunnel can be used, of course, not directly this tunnel, but there is some additional tunnels in the mountains as a research laboratory, because the height of the mountains above the tunnel is around 400 meters. So the conditions are very close to the underground research lab. So because underground research lab, they have usually the depth of 400 to 500 meters. So you have 400 meters of rocks above you. So it is the same conditions as underground with the depth of 400 meters. So that's why even if it is called, no, it doesn't called underground research lab, but it is in the list of the underground research labs. It is called Grimsel test site located in Switzerland. And it is some examples of the granite samples from our future site in the near the Krasnoyarsk. These samples was taken from different parts, not far away from each other, and you can see that it's quite big variations in the mineral composition of the granite samples, even in the, I would say, in the same area. So for the, as I mentioned, in Sweden and in Finland, there are two sites already very close to the commissioning for the final disposal of spent nuclear fuel. And in Sweden, design one of the engineered barriers. It is the cask made of copper. In our design, it is just stainless steel, but we don't dispose the spent nuclear fuel, we dispose vitrified high-level waste. We are planning to dispose vitrified high-level waste. Also, why the disposal of spent nuclear fuel is cheaper when the reprocessing of the spent nuclear fuel, because in this case there is a packing of the fuel assemblies without any treatment. Because when we put uranium dioxide in the fuel, it is very strong ceramic pellet, so with very low solubility, very good mechanical properties. So actually, inside our fuel assembly, it is already a good ceramic form for uranium and all the fission product. So there is no need to reprocess it or to treat it to solidify, because it's already in solid form, in good packaging, in water resistant material like zirconium alloy is very durable material. So, and there is additional water resistant material, copper. So this package is really enough for a long-term safety of the spent nuclear fuel cask. That's why, so there is no need again to reprocess this, to dissolve, to treat somehow this material. It is already in good form, just to put it in additional canister. So it is a Swedish design, and a few words about our future location in Russia. It is located, so it is Moscow, where we are now. It is the Krasnoyarsk city, so about 4,000 kilometers away. And there is a city of Zheleznogorsk, so it's not far away from Krasnoyarsk. It is around 50 kilometers if we take the direct measurement by road. It's around 80 kilometers. And Krasnoyarsk, it is the city with the population of more than 1 million people. So it's good transportation abilities, because there is also a Yenisei river, a big river that can be used for transportation of the radioactive waste. So it is more detailed map of our future disposal. So this is site that is called Yeniseiski. This territory, it is a closed city that is called Zheleznogorsk, and there is a river Yenisei. Previously, two another sites were also under consideration. It is Kamenny and Itatsky site, but due to some transportation problems, final decision was for Yeniseiski site, because for several reasons. One reason that it is already located inside the closed territory, so there is no need for additional security. Building fences, they are already there. And there is already a railway is constructed inside this territory. So there is no need for construction of additional roads and railways for radioactive waste. So from these points, the final decision was for a Yeniseiski site. It is so maybe a bit worse geological situation, because it is exo contact of the massive granitic formation. So you see that Itatsky and especially Itatsky site is located inside the this drop of the granite formation, but Yeniseiski is in the in the border between two geological formations, so that there are some cracks inside this site, but investigations showed that these cracks, they are how to say, they are not connected to the surface. They are closed inside this site, and it will be not they will be not affect the safety of the sites in general. So it is from the 150 meters, it is monolithic gneiss, massive. The surface facilities are located something like 4.5 kilometers from the Yenisei River. The depth of the disposal of the repository will be 525 meters, and it will be two layers of the facility of the repository. The first layer will be in the depth of 450 meters, and there is a 75 meters between these two layers. These 75 meters, it is wells between these two layers, where the casks or canisters with the radioactive waste will be placed on each other. So there is a general scheme of the facility. And the first step, of course, it is the construction of the underground research lab. Our colleagues who made the design of the facility, of the future facility, they, of course, analyzed a very broad, very large experience from the all over the world. So it is these points, it is different underground labs, not all of them, of course, for radioactive waste disposals. It's some geological labs, some labs for neutrino observation, etc. So there is a huge list of the analyzed underground labs. And there is our lab that is under construction. That is previously they chose this name ERLIC, so it is a acronym for Exploratory Rock Laboratory in Krasnoyarsk region, and also ERLIC, you can see that it is in mythology, Turkish Mongolian mythology, the ruler of the underworld. So it was some interesting name, but nowadays they don't use this name anymore. I don't know why, but they don't use it. It's just underground research lab in Krasnoyarsk region. So the just short the history of chosen of this place. The start of the geological survey was already in 1992. So I think more or less in all countries it is the same period. So in China maybe it was a bit earlier in 1985 or something like this. But I think after the Chernobyl and some other stories, many of the countries started to explore the possibilities for final solution of the spent nuclear fuel. Actually, it is interesting situation, because when the nuclear energy just started in the 50s and 60s, there was only few very small nuclear power plants, so there were no need at all for radioactive waste and spent nuclear fuel storages and disposal. But in 70s, when it was a very rapid growth in number of nuclear power plants, people realized that something has to be done with all these huge volumes of the spent nuclear fuel. And since the end of 70s, different approaches they were considered, and in 80s it was suggested by all the experts that the only way for safe isolation of the spent nuclear fuel and high-level waste, it is deep geological disposal. So at the end of 80s, this massive analysis of the potential sites started. So in Russia, it started in 1992, and in 2012, it was the final decision on the site that it will be in near the Zheleznogorsk city, Krasnoyarsk region, and it was debates about between these three sites, possible sites, and finally Yeniseiski site was chosen. So till the 2016, all the official events were finalized, all the required documents were collected, and they started to construct the underground research lab. They started it with the construction of the surface facilities. So actually today all the surface facilities, including the electricity grid, electrical grid, some administrative building, everything is already, they are already finished. And there is an active phase of the construction of the underground research lab. There is a boring of the 3 wells, each of the well with 6 meters in diameter. So it's a huge wells, and it's quite a complex task. So they started it, as I know, it is around 30 meters. They are already bored, but we are waiting for deeper wells. So, and of course, during all the activity, there is a public informing on the website of the National Operator for Radioactive Waste. And when the underground research lab will be finished, there will be a phase of the investigation in these underground conditions, but there are quite intensive investigation in the labs, in the surface facilities. So it doesn't mean that we just wait when the underground research lab will be constructed. We already have quite a lot of investigation of the properties of the rocks that are excavated from the boreholes. And by the plan, by the schedule, till the 2030, there should be a final safety assessment of this site and the decision about the suitability of this site for the construction of the final disposal of the for the high-level waste. So we will see how it will work. Also, I mentioned yesterday that in Russia there is we are the only country that that has specific or unique type of radioactive waste. It is liquid radioactive waste, and we have liquid radioactive waste disposal. So actually we have 3 of them. One of them is located in, so it is called Severny site also. So, and it is injection wells. There is a natural formation of the isolated water bodies, so they have no connection with other underground waters. So there is injection in this water body of the intermediate and low-level waste already for quite a long period of time. I think since 70s or something like this. So as far as it is quite a long history of operation of this unique disposal, there are a lot of data on the safety of this disposal, but still the International Atomic Energy Agency, so they approve this disposal, but only in Russia. They say, please, other countries don't use this type of disposal. So yeah. So another types of the disposal of the high-level waste that are now under assessment, under investigation. It is very deep borehole. So it is a scale. It is a typical deep geological disposal of the for high-level waste or spent nuclear fuel, and it is a deep borehole or deep well down to 4 or to 5 kilometers. So the idea that you don't need to excavate all the granite rocks, for example, from these depths. You just need to to dig a borehole with diameter enough to put a cask with the high-level waste or spent nuclear fuel. So small diameter comparing to 6 meter, for example, of the well. And you place cask with the high-level waste or spent nuclear fuel till, let's say, 3 or 2 kilometers in depth, and then close the rest of the borehole. So that means that you will have more than 2 kilometers of the natural barrier that will prevent the release of the radionuclide. So there is still questions and debates about the safety of such deep boreholes, because at this depth the tectonic movements can occur, maybe often, depending on the geological conditions. So what will be during these tectonic events? So nobody knows, and that is the question for the safety assessment of such boreholes. But still, there are quite a lot of investigation on this topic. Another example from the US company that is called Deep Isolation. It is, I would say, the combination of the deep boreholes and the conventional depth of the for the spent nuclear fuel and high-level waste. So you already saw that for deep geological disposal, the depth of 400, 500 meters is enough. So it is acceptable by all the experts. So the idea of the company that we don't need to make a very deep borehole. We can just make a horizontal well at the depth of 500 meters. So the same depth that is already accepted by all the experts, but we don't need to construct all these huge rooms, tunnels at this depth. Just the borehole where you place canisters. Also, they demonstrated already that they can put the cask with the radioactive waste, and they can take out this task from this borehole. So it's, I think, quite a good technology. But so they collected something like $30 million US dollars for this project. But I've heard about this experiment, about this demonstration, but actually I don't know what the situation now with this project. Is it accepted already or not by the government? So, but I think it's quite a good option. So, as we saw, there is several barriers for the radionuclide release in the environment. One of them is this geological media. Another important barrier, engineered barrier, it is matrix for the radioactive waste. And there are several types of matrix: glass matrix, cements, bitumen, and the crystalline matrix, or they also called mineral-like matrices. So for low-level waste and intermediate-level waste, the main type of the matrix is cement. It's a very good material. Also, it will be another lecture about this matrices. I will not go in details. Just a few words that we know cements in construction of the building for many, many years. So the technology for production, for the use, for different composition of the cement is very well known and very well investigated. So it's a very well developed technique, the cementation of anything. And of course, it was used for the cementation of the not only liquid radioactive waste. Actually, you can put in the barrel everything you want and put the cement inside the barrel, and it will be like a cement stone in the barrel, and all your radioactive waste will be in a good solidified form or compacted form. The only, maybe not the only, but one of the drawback of the cement is the presence of water. Yeah, and we know that by the action of ionizing radiation, water can be decomposed to different components, but final components will be hydrogen and oxygen. Of course, there will be some peroxides, hydrogen peroxides, other peroxide. These peroxides can interact with the radioactive waste, forming other materials, oxidize these materials. So the water radiolysis produce a lot of active species, let's say. So that's why cementitious materials cannot be used for high-level waste. Actually, we, not only we, but some group of people made research work on the stability of cement matrix, so the mechanical strength, the leaching of the radionuclide from cement are more or less the same even after the high doses of radiation, typical for high-level waste. But the only concern from the regulators is the formation of the gas from the water due to the radiolysis. So we cannot avoid the formation of hydrogen from the cements. That's why, at least at the moment, cements cannot be used for high-level waste. For high-level waste, we can use the vitrified form, so glass materials. And these glass materials, when glass is, let's say, synthesized or prepared at high temperatures, glass is a liquid material. So liquid material just poured in the barrel and solidified inside the barrels. Yeah, so this is like melt of the glass. And depending on the composition of the radioactive waste, we can adopt different combination, different components of the glass. So we will have different glass materials. For example, in Russia, as far as it was quite a lot of radioactive waste containing aluminium. It was popular to use the aluminum phosphate glass. And for example, the first high-level waste that are planned to dispose in Krasnoyarsk region, it will be aluminum phosphate glass from the Mayak enterprise. So depending on the composition of radioactive waste, you can change the components, the ratio between components of the glass matrix to have the better compatibility of the components of the radioactive waste with the components of the glass. Not all the radionuclides can be immobilized in glass materials. For example, molybdenum, sulfur, technetium, chlorine, they carbon, of course, they cannot be immobilized in glass. For these radionuclides, we can use either mineral-like matrices, or if the activity is not very high, intermediate level waste, we can use cement materials. The disadvantage of glass that why these elements cannot be placed in the glass, it is the formation of the crystalline phases inside the glass, and thus the formation of the points with the stress, and thus the glass become not very strong. It can be degraded to the dust. It can be a lot of cracks. Cracks actually is not a very big issue for the glass. It was an investigation of the vitrified high-level radioactive waste that was stored for 2 or 3 decades. I don't remember exactly. The glass itself was with cracks, but it was like a transparent glass. So the material was still amorphous with good leaching behavior of radionuclides. They tested it. So if there are some cracks inside the barrels, it is not the problem. The problem is the formation of such crystallites and formation of the glass dust with this materials, the concentration of the radionuclides in these materials. So for all the matrices, they are tested before they are selected for the further application. All of the metrics are tested with the standards. In Russia, we called our national standard GOST, so it's a governmental standard. And there is a list of the specific parameters that must be tested for the specific matrix. It is for cement compounds. Yeah, there is a leaching behavior of the cesium and strontium. It is the mechanical strength. It is the radiation resistance up to dose of 1 megagray. It is the thermal cycle resistance, because in repository we have hot and cold periods, seasons, according to our weather. So it should withstand the cycle, at least 30 cycles, like 30 years of the freezing and thawing. And it should have the same or enough mechanical strength, and also the water resistance. It is immersion of the cement compound for 90 days in water, and testing of the mechanical strength. It is more strict parameters for solidified high-level waste. It is either glass-like or mineral-like compounds or ceramic compounds. You see, if we compare the leaching rate for cement compounds, it's less than 10 to minus 3 gram per square centimeter per day. And for high-level waste, it is less than 10 to minus 5. And for cesium, 10 to minus 6 for strontium, 10 to minus 7 for plutonium. Now, this standard, the experts, they think to reconsider these parameters, and probably it will be changed. So the leaching behavior of these matrices will be controlled not by the leaching of the radionuclides, but by the components of the matrix itself. So how durable is the matrix itself towards in the water. So other parameters: thermal stability, radiation stability. Again, here is the dose 100 times higher than for cement compounds. And you can see also there is indication that radiation stability must be tested against the alpha radiation also. So higher mechanical properties, there is no gas released allowed except the release of helium. Yeah, there is a written except helium release due to the alpha decay. And there is some limitation for heat release. So this another matrix, it is a crystalline or mineral-like forms. If glass materials, they are amorphous and can be crystalline, and it is bad for them. For mineral-like matrices, it is vice versa. They are crystalline, and if they become amorphous, it is bad for them. It is enhanced leaching of the radionuclides, so it's a bad story. That's why all these matrices they are tested for the with the irradiation, either by gamma or quanta or electrons, or with the heavy particles. It is one of the example from my colleagues from the St. Petersburg, from the Radium Institute. They synthesized this mineral-like matrix based on the monoxide structure. So monoxide, it is the phosphate of the rare earths. Here it is a europium. And it contains 5 weight% of the plutonium-238, so with the short half-life, not very short, but shorter than plutonium-239. So it was synthesized quite a long time ago, and till the present day, so actually it was investigated 5 years ago, approximately. So at that time, the accumulated dose was already enough. So here I will go back. So the radiation stability must be tested up to 10 to 19 alpha decays per cubic centimeter. So it was this limit already of alpha decays accumulated in the matrix, and it was shown that even if this mineral from the X-ray diffraction analysis, the mineral was crystalline, so it was monocrystal, so very good crystalline form. But you can see that on the surface of these particles, there is a formation of the small particles, small flakes, and it was these particles were investigated, and it was shown that actually it is a pure europium phosphate without plutonium. So due to some effects, radiation effects, the structure, the whole structure, but the bulk structure of the monoxide stayed quite good, quite in good crystalline form. But on the surface, there is a changes due to the interaction of the surface with the moisture. So it was like a very small dissolution precipitation effects. So because these flakes, they were, even if they were europium phosphate, but the structure was not the monoxide, but rhabdophane. Rhabdophan, it is the hydrated phosphate of europium. So it's just the surface interaction. So no very big deal with the degradation of the material. Another story was with the glass material, also contained not 5%, but 0.5% of plutonium-238. It is borosilicate glass with the very nice color. My colleagues describe this color as a cognac-like color. And the interesting story that this glass was glowing in the dark. So this color, this red color, it is the self-glowing of this material in the dark. And it is the same material after the leaching test at 90 Celsius degrees in water. There is again the formation of the surface, some layers, but the bulk material again was quite stable. It was a glassy, amorphous material, only some surface modification of the glass. Another engineered barrier, it is a buffer material that is placed between the cask, between the canisters and the geological media in the repository. And there are several properties that are important for this buffer material. Again, next Tuesday it will be a detailed lecture on the properties, on all the properties of the clay-based barriers. So first of all, it is a limitation of the contact of water with the canister. It is there to prevent destruction or damage of the canister and the release of the radionuclides. And if there is a release of radionuclide, it is the absorption of the radionuclides to limit the distribution or migration of the radionuclides in the environment. Main characteristics can be again divided by technological and functional characteristics. So functional, again, it is let's say chemical properties of the material, like sorption, like diffusion of water through the material, like swelling due to the contact with water, formation of the colloids, etc. And technological parameters that are essential for technological applications, like the size of the grains, are they can be distributed easily in the closed space or not, etc., etc. The plasticity and all the other technological parameters. And depending on the composition, mineral composition of the clay, they have very different behavior, not only in sorption, but also in swelling, in their properties to extend their volume. And it can be clearly seen that the clay materials with high content of smectite or morillonite has very high swelling pressure. That means that when water will contact with this material, it will increase its volume very rapidly, in very large values. And they can create additional swelling pressure to the cask, to the materials. So it should be some combination of the good swelling materials and non-swelling materials, let's say, depending again on the design of the repository. The chemical properties, one of them is the sorption of the radionuclides. There can be different sorption sites in the structure of the clay minerals. But interesting part that sometimes very small additions of the impurities can change very much the properties, sorption properties of the material. It was tested with the clay from India, from the Kutch site. So it is, you can see here the sorption of the neptunium on the original non-purified clay from this site, and sorption of the neptunium onto purified Kutch clay. You can see the very large decrease in sorption, and the reason was that during purification it was the purification from the goethite that was only 3% in original clay, that was even difficult to analyze by X-ray diffraction, because 3% is let's say, limit for the X-ray diffraction analysis. We didn't see it in the beginning. Of course, the color, like red or orange color, so make us some guess that there should be some iron inside. But we saw this presence of goethite by Miss Bauer spectroscopy, so it was definitely there. So only 3% of goethite has this dramatic effect on the sorption behavior. So sometimes very small impurities can have very big impact. So you can see that these clay minerals, they have very, very different properties. And how to choose the correctly, or what is the best choice for the repository that you construct. It is quite a complex question. And several years ago, 4 years ago, the special program was launched by Rosatom. And our department was a scientific supervisor of this program. The program of scientific and technological support works to select the barrier clay materials for the implementation for further projects. So during this project, my colleagues, they created a database of the different clays that are available on the market. They tested it with 24 parameters, including sorption parameters, diffusion, density, technological parameters, so many parameters. And nowadays it is continuation of this program to use also some how to say, evaluation of the collected data for following task. For example, the ideal situation that when the designer of the repository, future repository or storage of radioactive waste already know the parameters that buffer material has to have. For example, density, swelling pressure, I don't know, diffusion of the water, filtration properties. He can go to this database, put these parameters, and it will be automatic advice what type of clays or what type of mixture of clays this designer can take. So it is the ideal situation. We try to reach this goal. So at the moment, there are quite intensive investigation of the properties of these clays for different application. So I hope we will reach this goal. And a few words about the links between the safety assessment and some technological process from the even spent nuclear fuel reprocessing. So we have this storage or disposal of radioactive waste, and the worst scenario is when the water penetrate inside the disposal, the cask, the canister degraded, the radionuclide released, and then this radionuclides goes to the environment. There are plenty of the chemical processes, chemical reactions of the radionuclides with the materials inside the repository, with the natural minerals. So there are plenty of the chemical reactions that control the radionuclide migration. So with the known thermodynamic parameters, as I mentioned yesterday, with the known thermodynamic parameters of all these reactions, we can build the model to predict the radionuclide release in the environment and to calculate the dose rate for the population from this radionuclide after 1,000, 100,000 years, what we would like to know. So with this model, we can build this forecast. That means that with this forecast, we can analyze what amount of the long-lived radionuclide, for example, can be placed in this disposal, to provide the safe to provide the safe isolation of the radionuclide. So these requirements can be used as initial points for designing and creating the new technologies for the treatment of high-level waste or spent nuclear fuel. So in a more simple way, for example, we know that the dose rate must be less than 1 millisievert per year for the population. That means that we create requirements for the composition of the radioactive waste inside the high-level waste. For example, it's not the certain number, say just an example. For example, less than 2% of actinides. With this information, we can build the requirements for the treatment procedures of the high-level waste and spent nuclear fuel. And with these requirements, we can already build the new scheme. So in this picture, I would like to show that all these numbers of these parameters that listed in the documents, they are linked to each other through maybe, so it's very simplified form, but I believe that it makes some sense and make it easier to understand all the connections. So again, brief conclusions that the radioactive waste, the result of any activity with radioactive materials. Radioactive waste can be classified or sorted by the specific activity and half-life, and further sorting by the aggregate state, by the technological processes. And fractionation or sorting of this radioactive waste can significantly reduce the cost of the processing of the treatment, the activity of the radioactive waste, and the time of the potential danger. And the most important issue in disposal, it is multi-barrier system based on natural barriers and engineered barriers. Today, main candidates for the storage or disposal locations, clays and granites, and in Russian Federation, they are granites. So thank you for your attention. If you have any questions, thank you. If not, when we can have a short break for, yeah.
For the modeling, those modeling projects, which software do you use?
In Russia, we have a licensed software called Gera. Gera. Yeah, it was developed by Institute for Safe Development of Atomic Energy of Russian Academy of Science. In Russia, it's IBRAE for Russian Academy of Science, and it is a licensed software for so we can use it to prove that our model. So not to prove that it is already proved, and we can use it for some official documents. This software. So there are different models in the software. Yeah. So for hydrological modeling, for atmosphere, they have another software. I don't remember the name, but they have several codes for different applications. For reactors also. Yeah. So they have, yeah.
So that monazite is used but have interaction with the liquids.
It's just with the air moisture. Yeah. But when we if we would use monoxide as a matrix, when we put it in canister, so there will be no interaction with the huge amount of air. Because these samples, they were stored just in lab conditions in open air, let's say, for 20 years. So yes, but it was the natural radioactivity of monoxide is not so high, and monoxide was chosen because there are natural monoxide minerals that are stable for more than 100 million years, and they're still crystalline. And as far as they have natural radioactivity, the total dose that is accumulated after these millions of years is more or less the same as for high-level waste. So and they're still crystalline. So it was an idea why these natural minerals can be analogs for matrices for high-level waste. It is monazite, zircon, and so some others. And my colleagues just decided to make this monazite sample. Yeah. Yeah. Also, they proposed to use this self-glowing glasses for emergency issues. So when you have no electricity, for example, you have this road signs of this radioactive glass, but of course it's not possible. Okay, yeah. So we have different operations. The final disposal, for final disposal, there is a company, not company, let's say company, that is called National Operator of Radioactive Waste in Russia. Know-how, yeah. Yeah, they are responsible for final disposal. So all the other enterprises and facilities, they must pack the radioactive waste in in containers, in the waste packages that must accept comply with this waste acceptance criteria, and then they transport these packages to the national operator. And then national operator must dispose it or store somewhere. So enterprises pay for this final storage or disposal, and that's the scheme. So we have, for example, a company called Radon. They are responsible for interim storage of the radioactive waste. For example, they collect our waste from Radiochemistry Division of Moscow State University. Once per year they come, they take our waste and they store it at their facility. And not only from us, but from other companies. It is only interim storage. But for final disposal, it is national operator, not Radon. Yeah. Okay. Okay. No, thank you again, and let's have a break till 12. Yeah. Thank you. Возьми, когда вопросы будут. Ну да. So, let's go further. In this topic, in this topic, in destructive characterization of radioactive waste, it will be mainly, of course, about the radionuclide content. We've just a short, brief introduction to different methods for separation and detection. For example, next lecture will be more specific on the chemical mechanisms of these methods. What we want to know about the radioactive waste when they will should comply with the waste acceptance criteria. It is not the full list, but the main characteristics. It is the content of radionuclides, of course, the dose rate, and the chemical properties different. And we will talk mainly about the content of the radionuclides. And before the destructive characterization, I would like to go briefly through the detection, through the measurement of the ionizing radiation. And just to remind that all the methods for detection or measurement of ionizing radiation, they are based on the interaction of ionizing radiation with matter. It's the only way to detect ionizing radiation. We cannot see it or hear it or to feel with any other our organs, but only by interaction with other materials we can see or measure ionizing radiation. There are different mechanisms or let's say results of the interaction of ionizing radiation with matter. It is ionization, excitation, production of the defects, and the energy absorption. So if there is a main mechanism, the production of the electric charges in the material, then we can apply voltage and collect electric current, and thus we can use semiconductor detector or gas field chambers. If the main mechanism is the excitation, so that means the emission of the visible light, then we can use scintillator detectors, plastic or inorganic detectors. If there are particles that produce a lot of defects, like alpha particles or other heavy particles, we can use the track detectors to visualize the pathway of the particles and to analyze the characteristics of the particles from these defects. Or we can, for very high doses of ionizing radiation, we can use the calorimetric detectors to detect the energy or heat that is collected inside the detectors. And two main characteristics of the detector, it is the efficiency of the detector and resolution of the detector. So here, what we measure, it is actually the counting rate, the response of the detector, the response of the our device to the ionizing radiation that is connected with the absolute activity of our radionuclide through this simple relationship. B here, it is the background of the radiation that is always present around us. There is characteristic of the radionuclide itself. So it is the probability or yield of the certain type of radioactive decay, of the certain type of the certain energy of alpha particles, for example, or gamma quanta, or beta particles, and this phi, the Greek letter, that is related to the efficiency of our detection system. That includes the geometry of the measurement, so how our sample and our detector are located with each other, how efficient the detector to this certain type of the type of ionizing radiation, alpha, beta, gamma, and the energy of this radiation. So there are quite a lot of parameters, but we can easily calibrate this efficiency with the standard sources, and thus we can just measure this efficiency. And resolution can be of different parameters. So in principle, resolution, it is the ability to distinguish between two events, either in time, so that then we can say about the time resolution of the detectors. That means that if one particle interacts with our detector, what is the time between the next particle that can be detected? Yeah. So if, for example, the resolution time is 10 microseconds, and after 1 microsecond, second particle comes to the detector, it will be not detected because there is still detector in non-steady state. It cannot detect the next particle. So it's sometimes we call it dead time of the detector. It can be resolution in some special resolution. So it is important for the track detectors, for example, when we visualize our particles, or resolution in energy. So when we try to analyze what the radionuclide emitted this energy of gamma quanta or alpha particles. We will see it a bit later. So efficiency and the resolution, they are the properties of the detector, and probably the main properties of the detector. Of course, there are economical, the cost of the detector, that is also very important. But from the technical point of view, efficiency and resolution. So what we use normally for to measure the radionuclide, why do we need the destructive characterization of radioactive waste? Some of the radionuclides, they emit, for example, only beta particles, and they are so-called difficult to measure radionuclides, because to measure them, we have to extract them, to separate them in individual state and measure them with either a liquid scintillation counting or some other techniques. So, or pure alpha emitters. Yes, the easy to measure radionuclides, it is gamma emitting radionuclides. Yeah, there is a very simple pre-treatment. You maybe make some, for example, dry the samples, and that's it. Yeah, to constant mass and measure it in some certain geometry. But for beta and alpha emitting radionuclides, it is almost impossible to use such technique without chemical separation, because the range of the penetration of alpha and beta particles is very small. Yeah, and if we just take a sample, it will be not possible to measure alpha particles, because they will not go outside of the sample. So for beta and alpha measurement, the best option, if we separate radionuclide individually, it is the liquid scintillation counting. It is the best option because it has very high efficiency, up to 100%. Of the measurement. Why it is so high efficiency? Because we put radionuclide inside the detector, let's say, because our scintillating media, it is part of the detector, and if we put the radionuclide inside of our liquid scintillating cocktail, we can say that it is a perfect geometry. All the beta particles are contacted or interact with the with the detector. So in this case, so it is liquid scintillation counting. We use a liquid scintillating cocktails. Cocktails means that the most part of the cocktail is the solvent. It is aromatic organic solvents, and scintillator with some modifiers, for example, the surface active substances that must help to make possible for water, aqueous solution, and organic solution to be mixed, and some other modifiers. So two main components again, solvent and the scintillator. And the energy of the beta particles, as far as the main component of the cocktail is solvent, the energy of beta particles first goes to the solvent molecule, then it transferred energy to the scintillator molecule, and scintillator molecule emit a visible light that is detected with the photomultiplier tube, so the device that converts photon energy to electric current. So this is the typical vials that we use for liquid scintillation counting. This plastic vial, glass vial, and it is specific vial that can be used for detection of gamma emitting radionuclides, but it's more like historical value of this vessel. Today I didn't see that somebody used it, only in some old papers. So it is a typical spectra from the beta emitting radionuclides. Sometimes we see these sharp peaks. It is not alpha particles. It is the conversion electrons, the electrons that are emitted from the orbital shells of the atoms, and that's why they have the certain energy, and the spectra looks like a very discrete lines, and very often people can think that it is alpha particles, but they are not. So alpha particles, the spectrum of alpha particles looks like this. So here two alpha particles, and you can see that. So this sample contain together alpha and beta emitting radionuclides. With the use of the electronic schemes, it is possible to distinguish between beta particles and alpha particles, and thus to separate spectrum of beta particles and alpha particles. So many of the devices can do it nowadays. What the problem with the liquid scintillation counting? It is the quenching of our sample. Quenching means that there is less photons that come to the detector than it should be. What the reason for the quenching? So first, the reason, it is so-called chemical quench. So if we have in our system some chemical molecules that can interact with the excited solvent molecules and take this energy and doesn't allow this energy to be transferred to the scintillator, so it catch the energy from the solvent molecule. So there is no excitation of the scintillator molecule, and there is no photon emitted. Yeah, so less photons than it should be. Another reason, it is color quench. So even if the photon is emitted from the scintillator molecule, this photon can be absorbed by some colored impurities, some iron, for example, or some dark organic molecules or whatever. And it is color quench or physical quench, and again we lose our photons, so we detect less photons than we should. This resulted in the shift of the spectrum to the left, because the less photons for the detector means less energy. So that's why we shifted to the lower energy part of the spectrum. And if it is low energy of the beta particles that are emitted, for example, for tritium, the lowest energy of the beta particles, then we lose a lot of photons and thus decrease in the efficiency of the detection. So quenching is bad for the liquid scintillation counting. We lose information about the activity of the radionuclide. But today again, it is quite a simple solutions. Let's say we just make a calibration curve of the quenching parameter. The quenching parameter can be calculated from the shape of the spectrum. And so we know this quenching parameter that again today can be measured by the device in automatic mode. And we know that if we have this quenching parameter, the efficiency of our detection is something like this, etc. You can see that for alpha particles, the quenching, the efficiency almost independent on the quenching, because alpha particles produce a lot of photons. And so for alpha particles, we can say that it is 100% efficiency of detection for even for very quenched samples. But for beta particles, for very low energy beta particles, so tritium has the lowest energy. It's 18.6 kiloelectron volts maximum energy of beta particles for tritium. But you can see that, for example, for carbon-14, that has also very low energy of beta particles. It is something like 156 kiloelectron volts. The efficiency already is not so dependent on the quenching parameter. Yeah. So the higher the energy of beta particles, the smallest will be dependence of the efficiency on the quenching of the sample. So let's say after 200 kiloelectron volts, you can neglect the quenching of the of your samples. Also, I mentioned that the electronic schemes can distinguish between the alpha and beta particles, because in case of the alpha particle, the signal decreasing slower than in the case of the beta particles. Yeah? Beta particles produce the signal and it decreases very fast. But for alpha particles, it's very long process of the decreasing of the signal from the alpha particles. So we can say that when signal stops here, it is only, not only, it is sum of alpha and beta particles, but all the signals that comes after, that prolonged after this time, it is only alpha particles. So then we can subtract alpha spectrum from the total spectrum of alpha and beta particles and obtain pure beta spectrum. So as I showed here. So it was done with this technique, but again, many devices today can do it in automatic mode. You just need to determine the best parameters for this discrimination of alpha and beta particles. So this parameter, or let's say the time after which we say that it is only alpha particles, this time depends on the energy of alpha and beta particles. So you just determine this parameter for best subtractions, for best discrimination. And with liquid scintillation technique, we can detect the beta emitters with the high energy of the beta particles without use of the organic solvent. So in this case, high energy beta particles produce so-called Cherenkov emission, Cherenkov light. For water, for example. So we know that there are no particles that can move faster than light, but only in vacuum. Yeah, so it is the let's say limitation. But in media, the speed of light is smaller than in vacuum, and the phase velocity of the light in the media can be calculated with this simple equation where n is a refractive index. So for water, refractive index is 1.33. So that means that in water, the speed of light only 75% of the speed of light in vacuum. And in media, it is possible for particles to move faster than light. And for electrons, they move faster than lights at energies more than 260 kiloelectron volt. So, and there is a short list, not the full list, but the most common radionuclides that can be measured with the Cherenkov counting. You can see that for strontium, and especially for yttrium-90, that is a daughter radionuclide of strontium, the energy of beta particle is more than 2 mega electron volts. So it is 70% efficiency of measurement of yttrium without any use of the scintillation cocktail. So in this case, we don't have a chemical quenching effect because there is no other organic molecules that can take this energy from the solvent because there's no excitation of the solvent. And so it is very nice technique. But there can be, of course, color quenching. If your sample is very dark, then there will be absorption of the photons by these color impurities. But normally after the destructive separation of the radionuclides, normally there are no colored impurities. So it's typical devices for the liquid scintillation counting. I think this one of the most popular in the world, this Perkin-Elmer machine, and nowadays Tricarb also belong to the Perkin-Elmer. And another company, Hydex in Finland. I think there are some other companies, but I think these two companies are the most popular. For alpha particles, if we have, for example, difficulties with the separation of individual alpha emitters, for example, americium and curium, it is very difficult to separate them. Thus, in liquid scintillation cocktail, it will be difficult to. So energy resolution in liquid scintillation is very poor. So these two elements cannot be seen separately in liquid scintillation spectrometer, but we can make a alpha spectrometry with very nice energy resolution. And if we know this energy that we detect, and we know energy of our radionuclides, energy of alpha particles that are emitted by our radionuclides, we can easily can say what type of radionuclides are in our samples and what the activity of these radionuclides. So the typical chamber for alpha spectrometry looks like this. It is a semiconductor detector, so silicon mainly. And the chamber, so here we place our sample, prepared sample, and then we make a vacuum inside because alpha particles has very short range. So the air will will make the detection very hard. So we make a vacuum inside the chamber and measure our good spectrum. Sometimes we make not very low pressure inside, but some higher pressure to avoid the interaction of recoil nuclei with the detector. So, and it is important for alpha spectrometry to prepare the good sample. Good sample means very thin and homogeneous sample on our substrate. Because if we have a bad sample with different, let's say, thickness of the sample, we will obtain these very long tails in our spectrum that can make it not so easy to calculate the activities of our radionuclides. To prepare good, very thin sample, we can use normally two techniques. It is either electrostatic precipitation of our radionuclides on the stainless steel disk or nickel disk or any other metallic disk. Or today it is very convenient to use a special filters with the thin layers of the cerium fluoride or barium sulfide. When we make solution through this filter, actinides are adsorbed, thin layer of actinide adsorbed on the cerium fluoride, and thus we obtain very thin layer of actinides. It's very convenient, but more expensive than this technique. But it is much faster and yeah, more convenient. So with the alpha spectrometry, we can obtain a very nice spectrum with high resolution of the energy of the alpha particles, and it is comparison of the spectrum with the liquid scintillation counting. Here you can see that it is much worse. Okay, and yeah, again, the typical techniques, devices for the alpha spectrometry. And I will not go through the gamma spectrometry. Here I just put one picture to demonstrate the differences in the energy resolution of different detectors. It is a semiconductor detectors and it is a scintillating detectors. So we can easily see that if we need to analyze the radionuclide content, I mean to determine which radionuclides are in our sample, then we definitely need the good energy resolution. We definitely need semiconductor detectors. But if we measure always only one radionuclide, for example, cesium-137 in all of our samples, then we don't need the semiconductor detectors. It's only one peak. We don't need the high energy resolution. We measure only one peak every day, and we are happy with just a scintillator detector. So it depends on the goal of the measurement. We can choose between different detectors. So now about the destructive characterization. First of all, we have pre-treat our sample. If our sample is liquid, then we concentrate our radionuclides either by evaporation or by some other steps. If we have a solid sample, when we dissolve or leach this solid sample to extract the radionuclide from the sample. Then, before the preparation of the counting source, we can choose between different methods for separation of the individual radionuclides for further measurement with the liquid scintillation counting or alpha spectrometry. Again, for gamma analysis, we don't need it. And to estimate the chemical yield of all of our steps, we can use tracers. So tracers are added with the known activity, and after all the steps, after the measurement of our sample, we know how much of the tracer we added. We measure our tracer, and from this data we can calculate the chemical yield of all of our processes, chemical interactions. So there is a list of typical traces for actinides. How we can destroy our sample? So it is either acid leaching, I think one of the most popular way for many samples. We can calcine our sample, heat it to the high temperatures. We can use microwave digestion or fusion. And these three methods, again, they are quite popular today. So fusion can be made with this Catanax machine. It is a mixture of our sample. Normally, it can be soil, it can be some rocks, it can be construction materials, it can be almost everything. Depending on what are you analyzing, about the chemical composition of your sample, the main chemical components, you can choose the flux for the fusion. So you mix your flux with your material, you stir it, you mix it, and then you put it in this small vessel and heat it up to 600 or 1000 Celsius degrees, and you obtain the melt, the homogeneous melt that can be further dissolved in acid or in aqueous solution. So it's the complete, almost complete in some cases, destruction of the sample with the good chemical yields. The microwave digestion and acid digestions, they are very close to each other. But in microwave digestion, from the name of the method, it is clear that we use the microwave oven to dissolve the sample. So again, we use some acids. It is very close to acid digestion, but we improve the efficiency, and we decrease the time of the procedure. So it is again more convenient, it is faster and more efficient than the acid digestion. And acid digestion, again, it is the very simple method. I think in any lab we are doing this acid digestion. You just put your sample in a glass, cover it with another glass, and heat it for several hours until it either completely dissolved or all the radionuclides are leached. So then, after the dissolution of the solid samples, we separate our radionuclides, and all the separation methods, they are based on the redistribution of the radionuclide between the two phases. It is either liquid and solid phase, it is precipitation and chromatography, or between two immiscible liquids, so it's liquid-liquid extraction, or between gas and solid, so it is gas adsorption or sublimation of the radionuclide. So precipitation. So precipitation, we know from the chemical course that it is possible only if our hardly soluble compound, if the concentration of this cation and anion can form the precipitates. That means that the product of the concentration of this cation and anions with this stoichiometric indexes is larger than the solubility product of our compound. If the concentrations are very low, so this product is smaller than the solubility product of our compound, then there is no precipitation. And sometimes, as far as our radionuclides can have short half-life, like 100 days, for example, then it is almost impossible to make a precipitation with them because the concentration is very, very small, 10 to minus 15 or 18 mole per liter. So there is no way to form their own precipitate. In this case, we use carriers. So it is compounds that help co-precipitate our radionuclides. There are three main types of carriers. It is isotopic carrier. In this case, we use the same element but stable isotope of our radionuclide. It is like co-precipitation of radioactive silver with just normal silver. It is specific non-isotopic carrier. In this case, we are using the chemical compound with the very close chemical properties, but it is not the same element. Yeah? So it is specific but non-isotopic carrier. And non-specific non-isotopic carrier, in this case, we use compounds with absolutely another chemical properties, but with very good, for example, sorption or co-crystallization activities towards our radionuclide. For example, iron oxide or manganese oxide, they are very efficient to catch actinide because actinides sorb on the surface of these hydroxides. So for concentration of radionuclide, we can use some specific carriers, universal carriers, I would say, to co-precipitate all the actinides, for example, or all the multivalent cations. So we can use this precipitation not only for concentration, but also for removal of the interfering radionuclides. And there is already a list of carriers that you can use for your specific radionuclides. Again, I already mentioned these convenient filters for preparation of the samples for the alpha spectrometry, with which use the mechanism of the co-precipitation of our actinides. So precipitation, the good part of the precipitation, it's very high degree of concentration. It's very easy to scale up this technique. It's very simple and convenient, and we can take carriers that are selective for our radionuclides. But there are, of course, drawbacks of every methodic. We need to use large amounts of carrier that the filtration sometimes it is time consuming, and precipitate can be contaminated with other impurities that have similar chemical properties to our radionuclide. Next, solvent extraction is a very common technique for hydrometallurgy, for processing metals in industry, and it is also very often used in organic, analytical, and other lab experiences. Solvent extraction, it is distribution of component between two immiscible liquids, and liquids, so sometimes water can be denser than the organic phase, or sometimes, for example, chloroform, it is a heavier liquid than the water solution. So both methods can be applied depending again on the solvent or the extractant that you are using. If you are using a non-polar extractant, then you use mainly oil, kerosene, or other light extractant. If you are using some polar extractants, compounds, then you use polar extractant. And just, I will not go in details with different extractants, it will be in next lecture, but just a few terms that we will use. So our initial solution that we called feed solution, our organic phase that contains extractant, our selective organic molecule, and diluent or solvent. After the extraction, we have organic phase that is called extract, and the rest of the aqueous solution that is now called raffinate. And if we would like to take our radionuclide back to the aqueous solution, we make a back extraction, or if there is a separation of radionuclides, we make it stripping, and this aqueous solution now called back extract. So the good points of the solvent extraction that it is a very technological process that is used in many applications. It can be very selective because we can vary the structure of organic molecule how we want. We can bring our radionuclide back to the aqueous solution, and we can use it for even very small concentration of the radionuclide. But drawbacks that we use very often toxic or flammable solvents. Very often we need several extraction steps. And of course, we generate organic waste. And in technology, it is organic radioactive waste. Next, chromatography. Chromatography, it is a dynamic process. So I will show it here. So we repeat the same procedure as in extraction mode, but several times by putting our liquid phase through the column with the sorbent. So it is a dynamic process with the multiple repetition of the single step of the separation. So it is very efficient in the separation, but we cannot use it for large amounts of the radionuclide because we have very limited capacity of the sorbents. And in principle, we can use different types of the sorbents, either organic sorbents that we call resins with different functional groups, or we can use inorganic sorbents like zeolites or some others. But yeah, and there is some parameters. So distribution ratio, it is how efficient the absorption of our radionuclide on the surface of the resin or the sorbent. And the separation factor is how efficient we can separate two radionuclides between each other. So it is, again, very simple and very efficient way to separate radionuclides. But again, there is not very high capacity of the sorbents. Sometimes we need to control the pH for the good separation of the radionuclides. And resins itself, they represent a very problematic secondary radioactive waste. And the combination of the liquid extraction and chromatography is so-called extraction chromatography. So in this case, it is the same method, the same process as chromatography. So it's dynamic process, so multiple repetition. But we can use the selective extractants, so increase the selectivity of our separation. And thus, a combination of two good sides of these methods gives us extraction chromatography, so very fast, very efficiency with higher capacity, but still not very high. So for high capacity, we use only liquid extraction or precipitation. As far as extraction chromatography use extractant, the properties of the sorbents are the same as the extractants as we use. How we put extractants on this resin? So the inert support or substrate for these resins is very porous media. So it is important to have very porous inert support. In this porous media, we put extractant. So we put our support in the solution of the extractant. Then we take it out and we dry it to remove the diluent from the pores. And thus, there is only extractant inside the pores. We can use also these vacuum boxes to increase the rate of the separation. So with the use of vacuum, we facilitate the stream, the velocity of our stream through the sorbent. So it makes it faster and still very efficient. Again, there is a list of the commercial resins, even the companies that create their own resins, they take the same names because these names of the resins from the tree scheme already everybody knows who did these experiments, and thus we saw some Chinese company, for example, that take the same names of the resin because to show that it is the same resin but from another producer. Just two examples. It is Teva resin. So we, not we, but there is a quaternary amine inside the porous media that is responsible for the interaction with the anionic species, anionic complexes of tetravalent and hexavalent actinides. And also it can sorb technetium, because technetium in heptavalent oxidation state presents as anion, pertechnetate anion. Another very important resin is a strontium resin. This crown ether is used in this resin, and it is important because it allows to separate strontium very selectively from all the other components, from cesium, from even barium and radium. You can see that at high concentration of nitric acid, there is a very high separation factor between the strontium and barium. So it is very selective, and strontium is one of the difficult to determine radionuclide. So good points. It is very selective, very productive method. Today there are some commercial resins that you can just buy this cartridge and use it for to separate your individual radionuclide. But the drawbacks, it is a very expensive one. Today the price is very high for these resins. These resins cannot be used multiple times. The producers write that it is only for one time use, but we know that it can be used 5 or 6 times actually. But still, from these spores, the extractant is step by step removed by the aqueous solution. So that's bleeding of the resin. But it's really very selective, and it's very convenient to use. So again, why do we need destructive characterization of radioactive waste? Mainly to detect, to measure the difficult to measure radionuclides, pure beta and alpha emitters. To make this separation of beta and alpha emitters, we can use different techniques like precipitation, co-precipitation, ion exchange, solvent extraction, and this novel, not all novel, but state-of-the-art, I would say, extraction chromatography. So, and vacuum box, I already mentioned it, it can really facilitate the separation, make the analytical procedure much faster. So thank you for your attention. If you have any questions, I will try to answer. If you have questions about the mechanisms, then wait, please, because next lecture will be about the chemical issues of these methods. But if you have any other questions, if not, sit.
Everyone.
I feel like I'm gonna sing. Do you hear me? My voice is better.
Yeah, but it's for online.
Okay, I didn't know that. Sorry. For difficult to measure radionuclides, it's very costful for the methodology. So for specific radionuclide, the methodology changes. I guess like with different. For example, you mentioned like tritium. It could be iron, maybe iron 55
Yeah.
or something. So, do you change the methodology to find the cost-effective solution, or you specifically need to?
Depends on the sample, because sometimes the matrix is very simple, and you need 1-2 steps to separate the radionuclides. Sometimes, if it is I don't know, natural sample, or if it is mixture of radioactive waste from, I don't know, 50 years of exploitation of some facility.
Decommissioning.
Yeah. It's sometimes it's very hard, and for this specific sample, we need to adopt the methodology. But if it's just, I don't know, seawater, for example, then there are already known methods to separate. Usually, we are talking about the new algorithms or new methodics only for very difficult tasks. Yeah. When we have, for example, tasks to determine the iron in the wall, iron 55 in the walls, for example, then it's another story. Yeah. So it depends on the sample, really.
Depends on the sample. Thank you.
Any more questions? If not, then thank you for your attention. And now we are going to the next lecture.
Тяжелая лекция. Можно работать. Hello, everyone. As I understand, my lecture is the most difficult because it's the last lecture before lunch. So, as Professor Petrov told, my presentation is quite similar to his because it's also deal with separation techniques. But I tried to focus on 2 points. One is mechanisms of separation of different species. And I also show you some real cases of implementation different techniques, solvent extraction, sedimentation, precipitation, and some types of chromatography. In case of radiochemistry, we can say that in general, there are some branches of radiochemistry where we need to separate radionuclides. First one is radiochemical technologies, a nuclear fuel cycle, when in the back end parts of it, we need to separate actinides from spent nuclear fuel, manage high-level waste. It's also a problem that deals with a separation of very different radionuclides. Another very important point is separation radionuclides for nuclear medicine. And the third one is radionuclides for another types of industries, for example, for gamma sources, cobalt-60 for gamma inspection, and so on. Here's the nuclear fuel cycle. And in the very it, when we mine uranium, it's in case of the different ores, it presents together with very different metals, different radionuclides. So that's why we need to separate uranium from these metals and also from its daughter radionuclides. And as I already say, in case of close nuclear fuel cycle, we need to isolate uranium and plutonium. Another very wide branch of radiochemistry and separation science is the production of radionuclides for nuclear medicine. Here you can see a wide range of examples of radionuclides that are used for diagnostics, for therapy. And in general, when we're talking about production of them, first part is irradiation by different methods, by charged particles or by neutrons in case of if we can use nuclear reactors. And after that, we have a problem of chemical isolation of certain radionuclides from target matrix, from byproduct radionuclides, and in some cases even from other isotopes of certain radioisotope. And as I understand, Professor Petrov, the main part of his lecture was about ways of determination and analysis of radionuclides and why it's important to make some different separations before measurement. This is my favorite example about determination of plutonium-239 in presence of excess of uranium-238. They have really different half-life times, and that's why when we compare such sample by this element by their activity, for example, uranium-238 have activity about 20 becquerels, and plutonium-239 is half a becquerel, and excess is 40 times. But if we recalculate this on grams and masses, we will see that such kind of excess is really higher, and in case of uranium is a 10 in 7 power magnitude. So it becomes very difficult to measure these radionuclides both by alpha spectroscopy and by ICP-MS. We will have problem that uranium-238 can react with hydrogen and give isobar that have the same mass than plutonium-238. So that's why before any measurement here, we need to remove excess of uranium. And in this case, if you make lower content of uranium in this sample, we can use alpha spectrometry. And but in this case, it will be still problem to determine plutonium in presence of uranium by ICP-MS. So it's really interesting because there are samples that can contain plutonium and uranium are very familiar to problems of back end of nuclear fuel cycle. And also in case of environmental radioactivity, when we need to measure, are there any problems with plutonium in the environmental, for example, in the areas close to facility when spent nuclear fuel is reprocessed. And another point when we're talking about separation of radionuclides is it's a very big problem in case of decontamination processes. When we have facilities, when we have some places that where we need to remove radioactivity to maybe use them one more time or make them safer. It's also a big problem to separate some kind of radionuclides or all of them from the different materials. And This is a scheme. It looks like difficult, and this is a scheme of overall process taken from this article. You can find it. And this is technique for determination of a wide range of radionuclides from environmental samples from water and also seawater. And you can see here it's really wide range, sludge, resin soils, plants, and so on. And why this scheme is so difficult? Because that radionuclides that present in environment, and we want to check their activity or even whether they are presented in the samples, they have very different chemistry, very different chemical properties. And that's why when we need to make such huge analysis, we need such huge scheme for such kind of analysis. Well, and this part of my presentation, maybe some slides are the same from Professor Petrov presentation. One more time, when we deal with separation systems, both of them, all of them, is a two-phase heterogenic systems. So we must have two different phases, or for example, in case of precipitation, this phase should occurs during chemical reaction. And one more time, this is the most widely used chemical techniques: precipitation, co-precipitation, solvent extraction, chromatography, and sometimes sublimation when we deal with substances that can be in can be gases in some kind of normal temperatures. Normal temperatures is that can be achieved in a laboratory scale system. Precipitation and co-precipitation. So the main problem in case of radionuclides in radiochemistry that radionuclides, most part of them, they have very low concentration, but the activity can be very high. And that's why it's impossible to precipitate them. And we need we need to use carrier. For example, his example of precipitation of radioactive silver, and it is really clearly see that when we deal with a solution with such kind of specific activity, its concentration is very close to its solubility product, and that's why even if we add concentrate hydrochloric acid, there will be very problems with its precipitation. And that's why sometimes we cannot use for precipitation the same substance, and we need to use some special additivities. So as I see, you already see the slides. So let's go next step. And also here some list of carriers that can be useful for separation of individual radionuclides or groups of radionuclides. So one more time about solvent extraction. It's a process of redistribution of two components between two immiscible liquid phases. We make a phase contact. Yes. After that, we can separate these phases because they're immiscible. And in this example, you can see that most part of the component that in the beginning of the process was in the aqueous phase, now in the organic phase. There is also some kind of back extraction, some kind of terminology for extraction process, solvent extraction processes. It's very important to say about solvent extraction because in English, extraction means very many different processes So solvent extraction or liquid extraction, not just liquid extraction. So here are some examples that after extraction, the water phase is called raffinate. And also, in general, after we extract something in the organic phase, we also need to back extract in the aqueous phase, because all of measurements and all of practical use of radionuclides, it implements the use of aqueous solutions. And now, in case of solvent extraction, it's important when we when we choose extractant suitable for solving our problem, for separate something from aqueous solution, from a mixture of different metals. Here we should understand what the nature of this extractant and what the mechanism that by what solvent extraction goes on. So the first one is so-called physical distribution. Why it goes on? Because for some substances, their solubility in organic solutions is higher than in case of aqueous solution. For example, iodine. Iodine is presented in a molecular with molecular structure. That means that these molecules are non-polar, and in general way it has low solubility in water. And maybe you know that the main technique to dissolve iodine in solution, it use mixture of alcohols and water. But if we put it in the contact with any organic substance, toluene, some aliphatic hydrocarbons and so on, this organic very fast becomes purple color. It's because iodine comes to this organic phase. It's a very colorful example of solvent extraction that goes by physical distribution, but it's also important because by such kind of things, extractant, not just extractant, for example, any low polarity organic compounds that can be present in the initial aqueous phase can go to the organic. Also, by this mechanism, water can also be extracted in the organic phase. Further, we will see that many of extractant it's polar molecules. That's why they can react with the molecules of water. First mechanism, real mechanism, is a solvating mechanism. How we can understand that organic compound, so here are they, for example, how we can understand that organic compound will bind metals and takes them into the organic phase. First of all, this organic compound should have long aliphatic chains to have solubility in the organic phase. But beside of solubility of extractant, this substance should make that complex with metal is also soluble in the organic phase. So this is examples, but the main idea that it have long aliphatic chains, and it also have some donating groups that will bind with metal cation. And in case of solvating mechanism, all of this group are neutral, so it's not charged, it's just neutral molecule. By this mechanism, we can extract metal salts, and it's also very important. Also, different acids can extracted by such kind of extractant. And here we can write down the extraction equation in very general form. Here you can see that this is a metal that in aqueous phase, counter ion for this metal, and extractant in organic phase. And after extraction, we have complex compound also in organic phase. It's important that for solvent extraction, we need to counter ion from water phase, and without it, there will be no extraction. It's an important point. We will discuss it a bit later. And here's some examples of extractant. Is the, in my opinion, maybe the most used extractant for radiochemistry. First one, the tributyl phosphate. Do you know where it used? Yes, extraction of plutonium, Purix process for isolation uranium and plutonium. It's the most massive used molecule in radiochemistry, because Purix process is industrial process when high amounts of organic phase and aqueous phase contacts with each other. Another example is also for phosphorus containing molecule is a triactylphosphine oxide. It's mainly used in laboratory scale processes, and both of these molecules is used in extraction chromatography. Another example is a methyl isobutyl ketone. It has only historical value. It was the molecule before tributyl phosphate that was used for reprocessing on spent nuclear fuel. It is very easy to produce such kind of molecule, but it has very critical drawbacks, such as high solubility in aqueous phase. It's easily to blow up with the nitric acid, and so on. Next mechanism is a cation exchange. That means that during extraction, one cation goes from aqueous phase to organic phase, and that's why molecules that can extract cations by a cation exchange, it's acidic molecules. So in general way, three subgroups of such kind of extractants is the phosphor-containing organosoluble acids. Here you can see three types. The main difference between them that they have different oxidation state of phosphorus, and that's why different chemical properties. And carboxylic acid, it's not so spread and used in radiochemistry and in hydrometallurgy because they are weak compounds, they have low extraction. Only one good thing I can say about them, that we can produce it from oil, and that's why they're very cheap but not very effective. And by this mechanism, we can extract metal cations and metal salts. And this mechanism is more difficult than solvation mechanism. Here we can also write down an equation for extraction by this process. And as we say, it's exchange. Metal go to the organic, and from organic, the protons go to the aqueous phase exchange. And another important points here. First one, that organic acids, and these groups is not is exception. When we put them in non-polar organic solvents, they have this part is very hydrophilic, and this aliphatic chains is hydrophobic. That's why when they occurs in the organic solution, they try to connect hydrophilic heads of these molecules, and in the organic phase, the aliphatic exchange goes. So in general, all of these acids are presented as dimers in non-polar organic solvents. And that's why the complex compound that goes to the organic phase, it has such kind of different structure. Here you can see that some hydrogen bonding, different types. This is coordination bond, this is ionic bond. And very important that after extraction, the concentration of protons in the aqueous phase goes higher. And it's an important thing that based on initial pH of the system, extraction can be very poor. If you have lots of protons in the aqueous phase, the equilibria will go to the initial state of this reaction. That's why this solvent, this extractants, is useful when we deal with high values of pH in the solution, about 2, 3, and 4 maybe. And this is typical extractants. It also phosphor-containing acids. One of them, DERPA, is also is phosphoric acid. I think after TBP, it's the most used molecules in the radiochemistry and also in hydrometallurgy. And more complicated molecule is the molecule HEHERP, and has PC bonding here. Sometimes this substance is called PC88A. And this is the most used acids from the very big list of different extractants. And as I say, carboxylic acids, even not just individual compounds, but mixtures that we can take from the oil, it calls versatic 10 because the sum of the carbons in these substances is equals to 10. And if we have cation exchange, we also have anion exchange. Here also driving force is the formation of organosoluble salt, but exchange of anions. That means that in organic phase should contain organic cation. And here you can see three types of the most spread substances. First one is a quaternary ammonium base cup. Is in the central part of it we have a nitrogen that have 4 bonds, and that's why it has +1 charge. And also here you can see an ion, and this anion goes to the exchange with some anion from aqueous phase. And also additionally 2 types of organic cations, but in laboratory practice and in the industrial implementation of such kind of extractants, the cup are most used. So the mechanism is right down here. It looks like close to the cation exchange. And in general about distribution, when we try to describe the extraction equilibrium, we use this value. It's called distribution ratio. It's a ratio between concentration in organic phase by concentration the same substance in aqueous phase. And if we try to highlight what the relationships between distribution ratio and some parameters of extraction system, it's a very complex relationship. The distribution ratio depends on pH, especially in case of cation exchange. It depends on concentration of competing anions, and also in the concentration of, in case of solvating mechanism, concentration of counter ions for metal, because if you make high concentration of these anions, the equilibria will shift to the extraction of the metal. It's the simple law of chemical equilibria. Also, there's some connection between distribution ratio and metal concentration. Very difficult relationship on temperature and so on. So solvent extraction is a difficult process, and can be influenced by very different wide range of parameters. And here are some real cases. The first one is the isolation of 2 radionuclides, actinium-225 and radium-223 from irradiated thorium target. First one, as we see in the first slide, the scheme is the scheme here there was very difficult, and this case is not an exception. Here we can see that only one part of the isolation of these radionuclides from target is a liquid extraction or solvent extraction. So why it is used here? The main problem is the general problem of isolation of radionuclides from irradiated target. That during the irradiation, the thorium, the mass of the thorium target is the same that before irradiation. That means, and concentration of radionuclides, target radionuclides, is very, very low. They have very high specific radioactivity, and in general, the usage is based on the radioactivity, not concentration. But in the first part, we need to remove the excess of target matrix from thorium. And for this purpose, we use solvent extraction, because solvent extraction can deals with high concentration solutions, high concentrated solutions. And that's why the first, after dissolution of this target, we can use solvent extraction, extract the excess of thorium, and after that we have two chromatography extraction columns, so, chromatography, to isolate the target radionuclides. And about chromatography, I think it's a very massive groups of method. The idea is the same on both of them, but the implementation is very different for different cases. And in case of radiochemistry and hydrometallurgy, the most used is the extraction chromatography and ion exchange chromatography. So the same slide as for Professor Petrov. So everything is clear here, and some maybe more pictures. In case of chromatography resin, here it's an example of it. It looks like such kind of compound. And the main part of ion exchangers and solvent and chromatography extraction resins, it looks like this. And the structure of them, there's two parts. First part is the inert carrier matrix, in which we put different functional groups. And depends on the nature of such functional groups, their way of connection is very different. For example, the most used chromatography resins, ion exchange resin, that contains sulfonic groups. Because it's very simple to put them in this structure, we just heat this copolymer with sulfuric acid for about 3 or 4 hours, and after that the sulfur groups goes to this copolymer. It's quite easy. And in case of exchange and again cation, both cation and ion exchange, the idea is the same. We put different groups that can deprotonate it, or some kind of organic cations on the surface of this polymer, and they act in the same way as we see in the solvent extraction mechanisms. And also solvent chromatography extraction. And this the main difference here that there is no chemical bonds between molecules of extractant and the surface. It's just van der Waals forces connect the polymer with molecules. And the synthesis is also quite simple, but the main problem that if it's simple to put this group on this surface, it's very easy to take them away. And when we deal with aggressive media, nitric acids, radiation fields, and so on, sometimes these molecules, they go from the surface of matters. And where we use chromatography, one more time, is the first part of nuclear fuel cycle, mining of uranium. And one of the way of mining is the leaching from the ore, even this ore in the Earth's crust. We put diluted sulfuric acid in the wells, and after that, uranium, different forms of uranium in ores, they dissolute because sulfur can easily bind it in the such kind of ionic complexes. And after that, we can bind these uranyl cations by so-called CG1 resin. It makes from carboxylic acids, and it works in the relative high values of pH. But you can see that selectivity towards uranium is very high in presence of different elements that can be presented in these ores. And after that, and by this process, we can concentrate their uranium solution from this concentration to 70 grams per liter. And different documentation cases. So we already see this process. And you can see that this is a process that have all of three type of isolation of radionuclides. And also you can see that solvent extraction in case of radioanalytical purposes, it's not so spread as precipitation and chromatography. And here is an example when we need to decomminate concrete waste. There maybe the most suitable technique is that heat treatment of it to remove the water to make the volume lower. And after that, we need deals with this cement and clear it up from the radionuclides. And so the main problematic radionuclides in this case, this is cobalt and europium. And after that, after dissolution of cement, we use precipitation by adjustment of pH to 9. And just by this simple procedure, we can obtain high documentation factors. Another example is some kind of sublimation of cesium. It's not easy to sublimate it, but when we deal with such kind of temperatures, we can expect that it will goes to the gaseous phase, and by this technique, if we have proper plant, proper machine, we can decomminate something, for example, soils from cesium-137. And this is example from India. This is process also for removal of cesium-137, and for this purpose is ion exchange is used, is chromatography is used. This is very high scale process, because by this process you can see that total activity that was removed by this resin. It's very easy to synthesize such kind of resin, and this huge amount activity of cesium was removed from the alkaline level waste that they obtained during the nuclear project. And I think that's all. Some brief conclusions. It's very close to the conclusions by Professor Petrov, but the idea is very easy because in case of analysis, in general, we use different methods of separation of radionuclides. In case of documentation, we still mostly used precipitation techniques. And in general, we should use different combination of all of these methods, especially when we try to isolate radionuclides from different irradiated targets or from spent nuclear fuel. So thank you for your attention. Maybe any question? So have a good lunch.